lecture we'll study an expression to compute voltage gain for inverting amplifier. In the last lecture we computed voltage gain for non-inverting amplifier and for a voltage follower based on op amp. Right, this is the sample circuit for inverting amplifier. We have a negative feedback and the input is also applied to the inverting terminal. That is why we call it inverting amplifier. Otherwise, if we apply input to the positive terminal, the non-inverting terminal, we call it the non-inverting amplifier. Right, in this circuit we have attached the non-inverting terminal to ground. That takes the inverting terminal to ground because it's a differential stage. The input stage is a differential stage. If we have connected this to ground, it will take this inverting terminal to ground too, because it contains two transistors connected in parallel. We studied in one of our previous lectures. So that provides a virtual ground, a terminal that is not physically connected to ground, but it has a voltage equal to the voltage of ground. So In is IF, In because it's ground, so In is the same as IF, right? So IF is this current. So In can be written as V in over Ri. IF is minus V out over RF, because actually V out will cause a current in the opposite direction, because this is ground, this V out is a positive voltage, so the actual direction of current is this, but we are considering to be in this direction, therefore we write it a negative. Right, and then solve V out over V in is ACL. It comes out to be minus RF over RI. That's simple. So even the closed loop gain of an inverting amplifier doesn't depend on AO for the case of a non-inverting amplifier we studied in our last lecture. So both inverting, the voltage gain expressions for inverting, and non-inverting amplifiers, they don't depend on AOL. In fact, they depend on the selection of RF and RI resistors values. A small example where we have this RF, we have to compute RF so that we can achieve a closed loop voltage gain equal to 100. So the magnitude is 100, minus means this is inverting. So putting these, Ri is given to be 2.2K, so RF comes out to be 220K. If we put RF, select RF equal to 220K, it will give us a closed loop voltage gain equal to 100 for this inverting amplifier. Right, the next is the impedance. We will talk about the impedance of non-inverting amplifier, the impedances of voltage follow, and impedances of inverting amplifiers in this lecture and in the next lecture to come. So when we talk about impedance, we will talk about both impedances, the input impedance C in and the output C out. So let's see what C in is for a non-inverting amplifier. Right, we'll start from the same point we started when we computed its voltage gain. Vf is according to voltage divider rule, Ri over Ri plus Rf into V out. It's a simple mathematics. So, and V out can also be written as AOL times Vd, where Vd is V in minus Vf, the difference of the voltage between the non-inverting and the inverting terminals. So up till now, the things are very easy and understandable. In fact, the whole expression or the whole derivation isn't very complex. Vf, in this expression, we can plug the value of V out here. Right, so it gives us Vf is equal to Ri over Ri plus Rf times AOL times Vd, where Vd is the difference of voltage V in minus Vf, this one. So what we can do now is that we can rewrite this equation so that Vf comes on the left hand side and the remaining V in minus Vd on the right hand side, and then we can replace, and then we can put the value of VF here. So V in minus VD is now VF, where we have taken VF from this equation. Ri over Ri plus Rf times AOL times Vd. So now we have this expression, everything is embedded in it. So now we can take Vd on the other side and can take 1 plus this as common times Vd. Since Vd difference, what is Vd? Vd is this voltage. This is In times the C in, the input impedance seen by the input impedance seen by the source that is driving this input, that driving this amplifier. So Vd is In times Cin. Vd, the difference of voltage, can also be written as the net current flowing into the op-amp times the input impedance of the op-amp. So replacing this Vd, we can replace Vd with In times Cin. So now the full expression is this as also. Now we are very close to the answer, very close to the value of Cin and I that we are supposed to calculate. So now we can divide this V in here, V in over In, and we are left with this on the right hand side, and V in over In, since we are working with a non-inverting amplifier, this that Z in for a non-inverting amplifier can be obtained by the Z in, where Z in is the Z in of the op-amp, the input impedance of op-amp given in the data sheet. Operation. It's a parameter of the op-amp. This is for open loop. So this open loop impedance is already very large. And what is the C in for non-inverting amplifier? This is already very large. The value, since you have divided this whole ratio with AOL plus 1, is meaningless. So this is a large value, even a larger value, a value very large. So a very large value multiplied by another very large value gives you a very large value. So Z in and I much greater than Z in of the op amp that we see in case of open loop operation. So the non-inverting amplifier gives us a control over the gain, as well as it increases the Z in of the op, that is a good sign. So I think there is an example for the students to solve an example given in the textbook regarding a numerical example given in the textbook regarding Z in more than the open loop Z in of the op amp. In the next lecture, we will study the output expression for the output impedance of non-inverting amplifier, and we'll study the input and output impedances for voltage follow and inverting amplifiers. That's all for this lecture. Thank you.